Hello everyone, today we are going to discuss about Wien's displacement law. Previously we have discussed about the Planck's radiation formula and now we are going to derive the Wien's displacement law from the Planck's radiation formula. So the Planck's radiation formula is U T 8 pi nu square upon C cube h nu e to the power h nu upon kt minus 1. This is the Planck's distribution law or Planck's radiation formula. So now we will write this equation in terms of lambda. For that we know nu is equals to c upon lambda, and taking its derivative d nu by d lambda is equals to minus c by lambda square. So for writing in terms of lambda, we can write this equation as delta d nu by d lambda. So this equation can be written as 8 pi nu is, in place of nu we will write c upon lambda whole square upon c cube h c upon lambda e h c upon lambda kt minus 1, and nu is equals to c upon d nu over d lambda is minus c. Minus we can neglect here, we can write c upon lambda square. We will take this, or we can take this like this, magnitude of it. So we get 8 pi h c upon lambda to the power 5, 2 plus 1 plus 2. So lambda to the power 5 is upon multiplied by hc e to the power sc upon lambda kt minus 1. So this is the Planck's radiation formula in terms of wavelength. Now from this we can get the Wien's displacement law. So Wien's displacement law is to find out the maximum of the wavelength with the temperature, means the behavior of the maximum of the wavelength with temperature. So what is Wien's displacement law? Wien's displacement law means lambda mt is equals to constant. So means we have to, lambda m here is max, we have to find out the maximum of the wavelength. So for that we differentiate this equation with respect to lambda and equate it to 0. Now write delta u by delta lambda is equals to 0. So delta u by delta lambda we are going to find out. Now 8 pi hc is constant, take it out. Now first we will take the derivative of this quantity, minus 5 pi lambda c, can write another one as same. Now taking the derivative of the second quantity, 1 annexing minus 1 e to the power hc upon lambda kt minus 1 whole square dot product e to the power hc upon lambda kt dot product hc upon kt minus 1. So dot means in multiplication, no vector and scalar quantities we are showing here. So this, which is equals to 0. So we will take the common things out. This is equals to 0, we can remove it. Now we take this factor common and lambda to the power 6 common. So we take 1 upon lambda 6 e to the power hc upon lambda kt minus 1 whole square common. So inside Also there are minus sign, we can neglect them by taking minus minus 5. Sorry, here are two minus sign, so minus minus, so this is minus 5 upon minus 5 into e to the power hc upon lambda kt minus 1 plus hc upon lambda kt e to the power hc upon lambda kt is equals to 0. So we get this. Now we can this factor also goes to 0, and now we can take this factor outside, then it becomes e to the power hc upon lambda kt, which minus 5 plus minus 5 1 minus e to the power minus hc upon lambda kt plus hc upon lambda kt is equals to 0. So this also goes to 0. We get this equation as 5 1 minus e to the power minus hc upon lambda kt equals to hc upon lambda kt. Now we can solve this equation numerically or graphically. So now we are going to solve it as simple as we can solve it. So we take hc upon kt as some constant alpha. Take hc upon kt is equals to alpha. So this equation becomes alpha by lambda is equals to 5 1 minus e to the power minus alpha by lambda. Taking alpha by lambda is equals to 5 minus epsilon, and substituting in this equation 1 we say 5 minus 1 becomes 5 minus epsilon 5 1 minus e to the minus 5 minus epsilon. So epsilon we can write here as nearly equal to 5 e to the power minus 5, which on scientific calculation we get 0.0337. Yes. So we get alpha by lambda equals to 5 minus epsilon. So alpha by lambda is equals to 5 minus epsilon, and which is equals to 0.0337, which is equals to 4.9663. So alpha by lambda is equals to 4.9663. Now since alpha is equals to hc upon kt is equals to 4.9663. So we can write here lambda 1 lambda t is equals to hc upon k into 4.9663. So this whole quantity is equivalent to some constant quantity. So lambda t we can write constant. This is we can write all lambda t we can write constant. Here lambda is lambda max, means maximum wavelength. When it occurs, it is inversely proportional. So lambda t is equals to constant. So this we can also find numerically, that using h value as 6.6 into 10 raised to the power minus 34 joule second, and k value as 1.38 into 10 raised to the power minus 23 joule per Kelvin, and c equals to 3 into 10 raised to the power 8 meter per second. We get lambda is lambda max 8.8 into 10 raised to the power minus 286 millikelvin on time. This is lambda max, means we are taking the maximum condition. So this is lambda max, t is equals to constant. So we can see from this relation that lambda max is inversely proportional to 1 upon t. So now in the graph, we have seen that if we are plotting spectral energy density with temperature, then this curve is like this. At t equals to, here it is new, t equals to 2000 Kelvin, and it increases, maximum of the curve increases with increasing in the temperature. That means maximum of the frequency increases. Here it comes at this point, here it comes at this point. So this is increasing, or lambda max is decreasing with respect to temperature. So both is nu max is proportional to temperature, and lambda max is inversely proportional to temperature. So using this relation, we can find out the maximum of the wavelength for the black body radiation curve, and for the maximum of the frequency, or if this maximum is given, we can find out the temperature, corresponding temperature. So this is the law determines the behavior of the black body radiation. Now we will talk about the photoelectric effect in the next lecture. Thank you for listening.